This is the aim of our mini contest today. Good morning, good afternoon, good evening, whatever you are now or you will be in the nearest future. Uh, we are running a mini course on computational metallurgy, and we'll try to understand whether what we have learned up to now, so some 3 hours before this meeting online, if it is enough to understand something which is useful for the applications as well. I believe it is. We will use just the software we have learned, which is founded from computer, but any computational metallurgy or computational thermodynamics software would work. Uh, we will see if today we will be able to meet with Bo Sudman and to try something with his open Calfad. I insist on using Panda because it has very good usability, and I believe it is worth of starting learning um, this kind of computational techniques. So I study to understand if we may or not apply our knowledge to understand tracking susceptibility uh, to some austenitic stainless steels. We will start with something quite simpler, if it is simpler, but we will start just with carbon steels with an oversimplification because we will consider only iron and carbon for this topic. We will consider some papers which have been published uh, in recent times or even a little bit earlier, and we will exploit the approach of Professor Sindo Cohn. As an expert in welding metallurgy, he has written a book and several papers, but what it is relevant here that he has been proposing in the field of welding, but in the field of solidification, which is a very complex topic, to use some graphs. We will understand which ones that relate the solidified phase fraction to the temperature. We are able to produce those graphs. We have already done it before, and we will do, or you will do it today. Mm, So we want to reproduce, well, this we can do, the iron carbon phase diagram, no problems in reproducing, and we have done it before in the solidification range and in the steel range. So we will use carbon content from 0 up to 0.7%, which covers most, even if not all, um, the carbon content of steels. Yes, there are steels with even with 1%, maybe in steels, but normally most of the steels are in this carbon content range. And we will just consider for the moment two chemical components, so iron and carbon. And we want to understand if we may reproduce or not this graph. So this is okay, this is a part of phase diagrams. But this is another diagram which relates lower or higher susceptibility, which is calculated by our software using our databases. And it is, you will need to read a couple of papers to understand this one. And this wouldn't take just an hour, or half an hour, like we are doing now. You should read some papers. So we will do the calculations there on the left and we will not do the experiments or review the papers which have been studied and presented in the past, but they've been discussed in several papers. So we want to understand whether we can understand this value, which for the moment sounds rather obscure, which is the derivative of temperature against Fs. Fs is the solid phase fraction, but this Fs solid phase fraction is raised to the 1/2 power. Uh, we should believe it. For the moment, we will go on, and this is another um, paper by a scholar, PhD student of Tayfun Sorisal. He's in Turkey, but he's been now, he's been working with Professor Sindaku. And in these graphs, he ranges grades of carbon steels and carbon steels neglecting manganese, silicon, and other minor contribution. And so these are 1005, 1010, 1070. So these are just steels with carbon content 0.1%, 0.15%, 0.2%, and 0.7%. And he has reproduced those graphs which relate the temperature with the solid fraction. If we would have, um, the beginning, we will use just solid phase fraction. This would be just a solidification curve. You know that you can model simply solidification by using the equilibrium solidification, which is the level rule, actually, or you can do something a little bit more difficult to understand for the beginners, at least, which is child solidification. What does it mean in simple words, just very quickly? When you have the child model, once the atoms are and the phases are solidified, you will not have any sort of diffusion in the solid state. So you see that those curves are different. Basically, they have the square root of the solid fraction here, but never mind, we will arrive to that. And you see also the ranking is rather different because if we believe for the moment that this maximum value of this derivative, it is an index of hot cracking, you will see that the worst behavior here, it is for 0.1% here, and then something that's similar to zero point 0.7 carbon content, so 1010 and 1070 steels. And here you see that those kind of grading comparing to shine solidification is completely different in values and in ranking as well. What we will use here is basically the shine solidification, but we will compare both level rule solidification for our austenitic steels and the shine solidification as well. And we will do our ranking as well in order to understand which is our possible good modeling for those situations. So let us try to reproduce uh, our first simulation together. So you should load the database FEMIANI 2018 TDB and select iron carbon and exclude those phases. Unfortunately, you have noticed these, which are diamond and graphite as well. So in your Pandat or in any kind of other software, you should just select iron and carbon, and exclude diamond and graphite. You have this is a database with different phases inside, and you should exclude just two of them. The database has several, I think 22 components. You have the ability to load in your own free version of commercial Panda, just three. But for the moment, that's pretty enough because we need a couple of them, iron and carbon. Okay. Once you have loaded those values, you should go into this small icon here, which is a symbol for casting from a ladle. You don't have to consider it. This is just the right icon for running a solidification. Then you can select the one you want. You can run equilibrium, never, rule solidification, or non-equilibrium child solidification. Here we have selected non-equilibrium, but it is just a matter of choice. And then we will run this value of carbon content, zero point 0.7, which corresponds to 1070 still. Of course, as you can see, you can reproduce non-equilibrium or equilibrium, just a matter of choice. And this is mm, the output of our lever rule solidification. Mm, you can compare the lever rules results in graphs which are given in the x-axis, the Fs, the solid phase fraction, which ranges from 0, so completely liquid, to 1, fully solid. And this is the solidification temperature. You see that the evolution lever is in blue and shine is in red is rather different. And now we want to reproduce results in this Fs raised to the half power, which is here, and in Pandat. I don't know if you can see this one. You just should add Fs raised to 1 half power in the tables, okay? You have the possibility, once you are running again this solidification, to see those values. Maybe I just shift and try to get mm, your version of Pandat. I want to insist a little bit on that in order for you to get all. So new workspace and phase diagram, database load TDB, Raffiniani, or it if you cannot find it like normally I do. Here is our database. Select your components, carbon and iron. Exclude your phases, graphite and diamond here, and here you put them there. Make your solidification simulation. We've been using 0.7 here. Click with the mouse, right mouse, and then you can replace the value with the remainder. It would not be difficult with the two components, but when you have 10 components like the commercial version, it's more difficult. So we'll use here equilibrium, and then we want to have extra outputs like there to have some more values in our tables. So we will insert these values uh, here. And now it crashes like normally if it is not so. This is the way you should do it. Shouldn't crash like it has not in there. So let us go back to our PowerPoint. So I was trying to show you and it has crashed. So let us go back to our uh, previous simulations and hope that your own Panda will not crash. I guess it has not crashed in my own Pandat. And so uh, once you have selected Fs here raised to the half power, you are okay. And then you plot those graphs with the temperature with the square root of the solid phase as well. You need then to use the value of the numerical derivative, the sign minus because it's better so you see on the top instead of your graph. So we will use this representation of the numerical derivative, which is double slash with a variable you will use for the derivation. So this is normally we see the epsilon on the x, normally in Italian. I hope it works like my interpretation mathematics also for you. But here we use double slash for the derivation, okay? And then we have added this in the tables, and we need to put into also the graphs, and we will reproduce such values for Fs, and I would like also to see with the square root of Fs. So let us go back and let us hope that I will be more lucky with our software and it doesn't need to crash any longer. Otherwise, I am worried because it would work not in the right conditions. Maybe it's too early for me in the morning that I'm not able to do something that I've done at least 100 times or even more. And here we are in the sleepy morning for me. This one value. You will use this value of the numerical derivative here. And sorry for the mess, which is partly due with the local time, which is 2 o'clock in the morning now. Okay, let's see if I can be successful. Finally, we want to build the graphs relating for the moment. This one graph is relating temperature to the square root of the solid fraction. Is okay. And then this is the first additional graph. And then I want you to show this one, which is the slope of the first graph. So this is the graph relating the square root of the solid fraction with temperature. And this is the graph relating uh, the solid fraction with the derivative of the temperature with the solid fraction. Okay, let us hope for the best. Okay, so you see here is the standard curve. We've been using child here, child rule with Fs and temperature, child root with the square root of Fs with temperature, and this is one, another curve here, and this is the slope of the previous curve, but with the sinus minus in order to get the maximum value of the derivative here, which is around 10,000 Kelvin. Okay, I hope you will do a little bit better than I've been doing here, but we will repeat it live possibly. So we can identify different values of this numerical derivative. If you read those papers, you will see that you should consider values between 0.9 and 0.98 for the solid fraction here. And now it is your time to work, and you should be able to reproduce those results to get a peak for this t versus fs to the square root on equilibrium conditions and on shy conditions using different carbo content from 0.05 up to 0.70 and possibly working with some other guy as well, working together. You should obtain those results. We will not consider this value shy with back diffusion because we should need more data on diffusion that we don't have in thermodynamics. So if you need to get some insight, you can read some papers. We don't have the time to read for the moment, but you can read yourself and try to understand this not very simple modeling, but uh, it splits uh, it splits results usefully in order for our calculation. So what we can do this is other these are other simulations you can add, like you have seen previous lectures, using different values of the solid or liquid fraction here. And this is again a child simulation. And and this is basically what we have done, which is the real question and topic that you should face today. Well, you should get some information reading those two papers, uh, and I want you to get this paper, possibly, if you have the possibility to read it. If not, I can provide it to you. Uh, well, uh, there are three sets of compositions here. One for aluminum alloys, one for nickel, and more contemporary and perhaps more. And the last one, as for steels, we will work on austenitic stainless steels with those compositions, and our aim is to understand which is their cracking susceptibility, both using the lever, so the equilibrium solidification, and the Scheil solidification. Back to page. Then we will be able to range those results. This paper is a further step in modeling. It uses some mechanical properties like an average modulus for those alloys. We don't have the possibility for now to do such a calculation in beginner's course in computational metallurgy. And what we need to calculate is those graphs for those 1, 2, 3, 4, 5 compositions, and you should reproduce this solidification behavior using the Scheil rule, and if possible, using also the lever rule. And this is your challenge today. I know that you don't have the possibility to model all the situation because you have the possibility to use just three components. So one possibility is to have a look of the results that I've already reproduced for you here. This is the web address, and you should open those worked out examples and see what's going on. And you can explode your tables, and then you can plot your own results. But as we have mentioned in the previous lectures, you can open your simulations and see which are the conditions which are inside your file. So let us go back to the place where I've left it. Here. And I should try to copy this address or just going there. You have a zip file there, and you will have this one. So this is the link which is reported in the PowerPoint. We will put it here. We will extract. I hope it will really extract it and not extracted all the files. So just a second, please be patient and let me find some tool to extract it properly. Here and now it's better. So you have extracted this directory, and you should will try to open this workspace. So inside Pandat, your own Pandat, let us clear everything here. File, open, workspace. And so this is cool, roulette, shine only. So here you have your workspace. You can view you can see the workspace window here, the database window, the property window, the message window, whatever. And so you will see for the three, for the five, not for the three austenitic stainless steels we've been employing. The Scheil, original Scheil graphs, temperature and solid phase fraction. If we click on the workspace, maybe we again we decompress our value. So we can view the conditions and batch file. So we can open the batch file which has been created by manual commands, actually. And here we see what has been done, which is possibly clearer in our PowerPoint there. Let us go. So here we've been loading our rolled child only zip file, decompressing it, and we've been opening with the file open workspace. Once we have this, and we have seen, possibly exported the and say the information in other more common, more used files like Excel, for instance, we can view our batch and that batch file, which has this PBFX, which is not easy to remember, extension, but there is an header here. You should not modify this. You should understand what is going on. So then you have database we've been using. So this is useful for you. And then I have selected because this has been done with the full version of the software. I've selected the elements I needed, so carbon, chromium, iron, manganese, molybdenum, nitrogen, nickel, phosphorus, sulfur, silicon, and titanium. And once I've selected those elements, I've also set the value for the first austenitic stainless steel composition. Uh, it is important to state that for this specific software, you should have all the sum, it is normal, all the sum of the chemical elements up to 100. So when you read zero, sometimes you should propose a, a, a possible value close to zero, but not totally zero. For instance, in steel, more than 30 ppms of titanium, normally it is not that much. And for instance, other values as well that you enter are possible, but these are based also on my experience of many years ago on making steel at an industrial level. So you should believe me that I'm using reasonable values. When it is written zero, we should not use zero for a series of specifications. So this is precisely our child conditions. So we will select another one, possibly lever, if we will not use it. And then here are the columns of our tables with the specific operation that I was a little bit not very efficient in producing the column names, but we have added those values, the derivative of temperature with the solid fraction, the derivative of temperature with the square root of the solid fraction, all with the sign sinus minus, and then another column name, which we have used already for the x-axis, which is fs raised to the 1/2 power. So these are the tables. I would add in this slide, I would add some space for the graphs because these are the data for the table. So let us try to duplicate, to cut those values here and to go inside our database and go into uh, graph result, which is this one. So our graph, just one, it has the x-axis with fs and the y-axis with t. Let us save with this value. It's not so important. So we have now the possible values to insert in our context. So my motivation, this is a solidification curve. We are in the range solid fraction from 0.19 to 0.99 for the value of the derivative of the solid fraction using this criterion. In our course, we will see now that this derivative is also useful and that the derivative is also useful. This is a picture from a recent paper, and this is a possible interpretation for solidification cracking or solid state cracking here, which is close to the concept of semi-solid processes. And this is related to grain formation on rapid solidification in industrial condition, for instance, die casting using die. So for the moment and for the time here in Italy, that's nearly all. But for those of you who have never met or have forgotten what it is, a stainless steel, this is taken from an Italian textbook by a colleague of mine, Marco Boniardi, and also another her researcher, which is Andrea Casaroli from Milan Polytechnic. And one of my former students has reproduced those ebook in a short way for this presentation. So you will find all the details and all the story on stainless steels here and here, and you can browse maybe too many information on that. The book is available for free online, and if you want to get the book instead of the PowerPoint presentation of my student, it's okay. But then you will get what does this name austenitic stainless steel mean, or ferritic or whatever. For the moment, it's all. I will try to get to sleep, and hopefully, uh, I think I'm finished. So I can interrupt the screen, use the webcam for a while at least. Wish you a good day, afternoon, whatever, and see you possibly later on. Okay, see you.